Okay, so let's try the next coding exercise. So open the leetcode.com and go to the problems tab, and in the search question number 530. Hit enter. So we have the question 530, minimum absolute difference in BST, and it's come under the easy category. So click on it. So let's read the question. So it's the minimum absolute difference in BST. BST means binary search tree. So the question related to the tree, and specifically binary search tree. Okay. Given the root of a binary search tree, so we have a root is given. So if you see the function definition is given. In that we have only root is given. Okay. Return the minimum absolute difference. So absolute means like basically the positive difference. Absolute difference between the values of any two. So this is the like the main keyword, absolute difference. Absolute difference between the values of any two different nodes in the tree. So, and we need to find the minimum absolute difference. So basically, what are the all nodes? So let's take the example number one. So 4, 2, 1, 3, 6. So what are all the nodes? So if we create a list, then 4, 2, 6, 1, 3, then we need to find the like minimum absolute difference. So minimum like if we do 4 minus 2, then we are getting 2, and if I do 2 minus 4, then we are getting minus 2. But we don't need to include the minus keyword. Like we can like if even if we subtract 2 minus 4, then we can call it as a 2, even though answer is minus 2. But if we use the absolute function, then it will going to give the positive response. All right. So like that's why like they said, don't worry about the whether you are expected 2 for 6 or 6 for 2. The difference should be like the same. Okay. So you need to return the minimum difference. So we have like 3 and 4 and 5 nodes. All right. So how you are going to calculate the minimum difference? So first we should know all the nodes. What are all the nodes? All right. Then what we can do is we can like get all the difference like as a minimum approach. Like first thing like what comes in our mind. What comes in our mind is we what we can do is we can create a list of all the nodes, and then we can do the difference as an example. So look at this diagram. So we have this tree. What we can do is we can create a list. Uh, how we are going to create a list? By traversing through the list, by traversing through the tree. So by any method you can traverse through the tree. So let's suppose 4 will come here. So we are store the 4. 2 come here, we store the 2. 6 come here, we are like we are traversing level by level. So 4 come, 2 come, 6 come, then 1 come and 3 come. Okay. So 4, 2, 6, 1, 3, we have the list. Now we need to find the minimum difference between any two. So it's not the adjacent. If it is the adjacent, then the question will be different. It could be any two. So how we are going to? So we need to find the difference between 4 with all the elements. 4 with 2, 4 with 6, 4 with 1, 4 with 3. We need to find all the difference. All right. And 1 minute. So we need to find all the difference. So how we are going to do? Okay, we are going to run like two loops. Okay, 4 minus 2, 2, 4 minus 6, 2. So basically 4 minus 6 is equal to minus 2, but we need to take the absolute difference. So that's why we are saying 2. 4 minus 1, 3, 4, 4 minus 3, 1. Okay, so we have got the like the values. Then 2 minus 6, 4, 2 minus 1, 1, 2 minus 3, 1. Then 6, 6 minus 1, 6 minus 3, then 1. 1 minus 3 is equal to 2. Then 3. So there is no element further. So we are not going to. Then out of this, what is the minimum value? We have the minimum value 1. So 2, 2, 3, 1, 4, 1, 1, 5, 3, 2. We have the minimum value 1. So we are going to return the 1. So this is the like the first approach comes in our mind. But if you try to solve this question, like it's easy category only. Like we can solve this question. We can like traverse the tree. We can store into a list, and then once that we get the list, we can run two loops. Like first, because we need to do the subtraction from 4 with all the elements, then 2 with all the elements, then 6 with all the elements, then 1 with all the elements. So we can run the two nested loops, but the time complexity will be more. All right, and maybe we will get time limit exceed uh, uh, in any of the test case, like when we are going to submit the solution. But can we do some other approach? Just a little modification, just a little modification only, but everything is going to remain same. Can we do that? Like, so the answer here is yes. So right now, let's suppose, okay, let's suppose we have this list 42613. But if we sort this list, if we sort this list, then we will get 1, 2, 3, 4, and 6. 1, 2, 3, 4, and 6. So this is the sorted list. So this is the sorted list. If so, you can sort the list like using the sort operator or the sorted function. All right. So we are get the list. So 1, 2, 3, 4, 6. Now, if you get the difference, so here what we are doing is we are subtracting like 4 with 2, 4 with 6, 4 with 1. In this case, when the list are sorted, so if we are going to subtract 1 with 2, there is no need to subtract 1 with 3 because we know this is a sorted list. So the difference between 1 by 2 is definitely less than the difference between 1 and 3. Right? So if we are sort the list, then what we can do is we can like get the difference of the adjacent nodes. So 1 and 2, right? So 1, 2, and 3. Because like there is no need to do the difference between 1 and 3 or 1 and 4 and 1 and 6. Definitely though the difference will be the more. So we can just do the adjacent differences 3 and 4 and 4 and 6. That's it. So like we will like only within a one loop we will get the difference. Okay, this is the our output. This is our output. So this is the one solution. Right? We can do that, and we have to like as a first approach we will do the same thing. But like there is a one more like thing. But what we are doing is first we are like traversing the tree level by level. So first we are storing 42613, and then we are like performing the sort operation, and then we are running a single loop. But can we directly generate the list sorted list? Can we directly generate the sorted list? So the answer is yes. Why? Why? How? Like how we are going to generate the sorted list and why? Because this is the BST, this is the binary search tree in the question. In the question, it is mentioned is the BST binary search tree, and there is a property of the binary search tree is the left side element is smaller than the root, and the right side element is larger than the root. So what we can do is instead of the level by level traversal, we can do the in order traversal. So in the in order traversal, first is left, then root, then right, then right, right. So then right. So we can do the in order traversal. So if we do the in order traversal, so first is 1, then root, then 2, then 3, then 4, and then 6. So using the in-order traversal, we can directly get the sorted list. There is no need to do the first level order traversal and then do the sort operation. Right? Then we can do that, but the time complexity unnecessary will be more. But we have like lot of traversal method. We have level by level traversal method. We have in order traversal. We have pre-order traversal. We have post-order traversal. So we can think like, okay, we need the sorted. So we know this is the binary search tree. So what we can do is I can do the in order traversal. So the in order traversal first is left, then root, then right. So then this four element, then six. So at the end, I will get the like a sorted list. So basically, like this thing, this whole picture, this whole picture I can avoid. This whole picture I can avoid. I can directly generate the sorted list. So let's try to do that. Like what we can do is we will have a tree. We will perform the in-order traversal. We are going to generate a sorted list. As soon as we get the sorted list, then we can do the difference. But first, our approach should be the how to get the sorted list. So let's do that. So we need one list. So we need one sorted list. So let's take a temporary list. We need a one sorted list. Okay. Now, now what next? So we are going to store the elements into the list, but which element? First, we need to do the in order traversal. In order traversal. So, okay, so let's do the in order traversal. 1 minute. So let's do the in order traversal. So def in order, in order traversal. Okay, if we need to, we will need to do the in-order traversal. We will do something, and we need to call this function in order traversal, and we have the root. So we will start from the in-order traversal from the root only. Root only, fine. Now what next? We know in the in-order traversal, first is left, and then root, then right, then right. All right, so this is the in-order traversal. So the same thing we are going to do. We will do using recursion. So first is left, so we will call the same thing on the node dot left. Okay, then so okay, we can do if node. If node, then only do this. Okay, or you can write the base case. So in order traversal, first we will call that on the left hand side, then the root, then the right hand side. So we have to call on the node dot right as well. All right, and in the between we need to we have the root. So in the between we have the root. So like let me show you. So like we started from here to this element. We said okay, do the in-order traversal on the node dot left. So it will do the traversal on the node dot left. So it come here. Now we said okay, we call her do the traversal on the node dot left. Then it will come here. We tell here okay, do the traversal on the node dot left, but there is nothing. Then we get this element, and we need this element only. We need this element only one. All right. So as soon as we get the one, we need to store. As soon as we get the one, we need to store. Right. So what we have to do? So we have to do temp list dot append and node dot value. So we are going to store it. So if you do that, if you print it, just we are going to print it, like whether we are printing the correct list or not. Time zero. So let's try that. So we could see we are printing the correct list 1, 2, 3, 4, 6, 1, 2, 3, 4, 6. And if you see case 2, we are printing the correct list. Like in the case 2, like 0, 1, 12, 48, and 49. So we are printing this sorted list. We are printing the sorted list. So we got this list. We already got uh, this list. Now what we have to do? We have to run a loop, and we need to subtract 1, 2, 2, 3, 3, 4, and 4, 6. So we need to run the loop till this point because, all right. So how to do that? So let's we will get the list. Now we have to run the loop. So let's do the minimum. So let's we have to calculate the minimum difference. So let's assign it by default as a maximum, but the maximum value infinity. Okay. Now run a loop for I in range of a range of length of temp list, or even you can like calculate here n is equal to length of temp list, and you can just put here n. But if you put here n, then it is going to run the loop till 6, and for the 6 there is no further element, so we need to run only till 4. So n minus 1, and that's it. Now we need to calculate the difference. Minimum difference is equal to minimum of whatever the difference, whatever the difference, and this element and this element. So how to get the element? So temp list I plus 1 minus temp list I. So we will get the difference, and at the end we are going to return the minimum difference. So let's try to run it. So our sample case has been accepted. So let's try to submit. So our solution has been accepted. Our solution has been accepted, and all the test case has been passed. And in the question, there is nothing as such mentioned. You can't use the extra space. So that's why we are using the extra space. But but can we avoid even using the extra space? Can we avoid using the extra space? So the answer is yes. We even don't need to store the elements. Why we don't need to store the elements? Because if you closely see what we are doing, we are just subtracting the adjacent nodes. We are just subtracting the adjacent nodes. Like we are just subtracting the adjacent node. So and I am doing the in order traverse. So as soon as find one, right, there is nothing. As soon as find two, I can store the previous element and then I can do the subtract. Then I will reach 3. I can store the previous element. Previous is 2. Then I can do the subtraction. Then I reach 4. So previous element is 3. Then I can do the subtraction. Then I will reach 6. The previous element is 4. Then I can do the subtraction. The same thing. But instead of that, I don't need to store that element. So how to do that? Let's do that. So in this case, we don't need the temp. We don't need the temp. We need the minimum difference. And we need the in-order traversal as well. But we don't need this, and we need to return the minimum difference. We need to return the minimum difference, and we definitely need the in-order traversal because we need to traverse the in-order way. But how to do that? Uh, so first we will get like node dot left. Okay. Now, in this case, like earlier we are storing. So first element we store one. So now we get one. So from where we are going to subtract? Nothing. We are not going to subtract here. So what we can do is we are going to store as a previous element. So element is a node. Then it will go to right. So 3. Then sorry, it will go to root. So like 2. So now every time like previous element is storing as a 2. All right, so we are not like subtracting. So what we can do is I can store the previous element. Previous element is equal to none. All right, because for one, there is no previous element. So that's why I'm saying previous element is none. So as soon as I get one, here the first element I will get one. So as soon as I get one, I don't need to subtract. If I get something else, then I will get subtract. So what I can do is if previous, then only I will subtract. Then only I will subtract. Minimum difference is equal to minimum difference minimum difference, and we need to subtract. So what we need to subtract? Node dot value minus previous dot value, right? And we will get the minimum. So basically, in starting as soon as we are going to traverse, so first we get one, but for the one, we are not subtracting anything until unless we are not reaching two. So there is nothing. We are not subtracting anything. So previous is none. Previous is none. So here previous is none. So that's why we are taking previous none, and we are saying if previous. So for the first case there is no previous, so it will not even go, and we are storing the one as a previous node. So we are storing as the one as a previous node. Now in the second case, when it reaches two, when it reaches two, then we have the previous because we already stored the one in the previous, then if the previous, as soon as we get, then we are going to store the difference. That's it. So basically using this approach, the same thing we are doing, the same thing we did in the like when we are like running the loop on the array. The same thing we can do, but instead of storing the element, we can do like during the in-order traversal only. So let's try to run it. So if you run it, now maybe you will find some issues. Yeah. So the issue is you see the local variable previous. So the previous is the local variable of this function. But this previous and this minimum difference we have defined in the outer function. So how I am going to access this? So what I can do is I can define that as a non-local previous and minimum difference. So what is non-local? So non-local like same as the global keyword. So non-local is a keyword in the Python which gives you the access of the all the variables of its parent function. So this is the child function. This is the parent function. So if you want to access the variable of the parent function into your child function, then you can use the non-local. So let's try to run it. So let's see. So our sample case has been accepted. So now let's try to submit. So our solution has been submitted. Now this time you could see earlier we like consume so much memory. Now we are not using a lot of memory. All right. So our solution has been accepted. So it's like uh, you can say a easy question, but a little you need to think. First approach, definitely we can come in our mind, okay, let's store all the nodes in a list and then do that, or sort it, or even without sort it, just run like two nested loop and we can get the minimum. Definitely we can get the answer. So there is no nothing wrong with that solution. But maybe like some test cases might not work because of time limit exceed. Then we can think, okay, why we are doing level by level traversal? Why can't we do the in order traversal? Because this is the BST. Yes, we can do the in order traversal. So we are directly doing the in order traversal. So we like can skip this stage. Then we get this. Then one thing also come when we are only subtracting the alternate. Then why can't we subtract like just like when we are traversing? Because we just need to store the previous node. Like as soon as I reach 2, I only need the previous node. As soon as I reach 3, I only need the previous node. Then same thing we are doing. The same thing we are doing. So then in this way, we are like even removing the extra space. So that's it. That's the end of the video. Thank you.